we'll obviously start with Andrew, our CEO of GTS. He'll do a small welcome and really look at place setting the whole event and giving some history to what we're actually foreseeing now. Chris Wojcik from PICE, one of our obviously technology partners, will look at various observations around the world, trends and challenges. And when we put the format of this agenda together, I did want to highlight the fact that PICE is doing applications around the world. Some of those GTS have been involved with from an engineering perspective, and would be good for this session for people to understand what else is happening outside of Australia. We then have Lee from Horizon Power, who is going to present, if I can call it a be there and done that type presentation from the implementation and the journey that's been happening now for just over 2 years. So that'll be a very interesting presentation. I've seen the format and I think you'll really like it. Patrick Lee, the president of PICE, will look at applying the lessons learned, obviously at Horizon Power, but also aspects of how that is, drafting if I can call it an introduction of DERs around the world. So everyone has been looking at what's happening at Horizon Power and then determining how that can be implemented through various other aspects of either microgrid or DERMS across their requirements or their distribution or transmission network, or the generation of and supplies of DERs throughout Australia and throughout the world. If we do have time for Q&A, we'll introduce those questions that have been raised through the chat, and then I'll close it off towards the end and stop the recording. Just a quick introduction of GTS for those that don't know GTS. We provide specialized real-time systems integration and data expertise. That is our forte. That's what we are primarily focused on in delivering for our customers. And we do have an aspect of ensuring that we engage with customers and drive value in the delivery of projects and solutions based around the implementation of DERs, but also primarily around the management of real-time data and the integration of that data for the better use within the organisations that you currently work in. Just as a point of reference, we're the largest and most accredited OSI self-PI system integrator in ANZ and support all of our technology partners locally. So our goal is not only to represent our partners, but to support all the applications that we deploy with our partners. So every customer has localized support for all applications that we deliver. And just to have all the further reassurance as part of the growth for GTS, we have people represented in all cities in Australia. So you have somebody to talk to locally or somebody to have a coffee with locally, which is a strategic move on GTS to make sure we have that, personalized presence no matter where you are. That's primarily it from a summary perspective. From a GTS and housekeeping perspective, I'd like to introduce our first speaker, Andrew Todd. Andrew, if you could share your screen, please. Or I think you may just want to hold this screen. I'll hold it until you finish talking.
That's fine. I don't have a screen to share, but I will share my camera, Steve. Thank you for that. I'm going to reflect a little bit on the history of renewables in Australia, particularly rooftop solar, which many of you will be familiar with. But I thought I'd share a little bit of that today as background because it actually had an effect on our strategy and in a roundabout way led us to this conversation today. So in 2001, the federal government introduced a renewable energy target to generate something like 9.5 gigawatts of Australia's energy through clean power sources by 2020, which was about 2% of the expected total at the time. And part of that renewable energy target was the small scale renewable energy scheme, which incentivised domestic solar installations, effectively subsidising owners to reduce the costs. And that was done in anticipation that there would be reductions in costs for generations, things like new coal and gas generation and new transmission lines. And that incentivisation led to larger uptake in solar systems, which in turn drove the market to invest more to improve the technology and manufacturing costs. Solar silicon dropped by something like 80%, and those cost reductions further fueled the uptake and the demand. And despite these subsidies easing off, the domestic market shifted to larger and larger systems. We had an average of about a 2.6 kilowatt system, and it's now something like almost a 9 kilowatt system. That's the change that's happened over the past 10 years. And according to the CSIRO, Australia now has the largest uptake of solar in the world, with about 30% of homes fitted with solar panels. That's more than 2.6 million rooftop systems as of December last year. And for perspective, the Australian Energy Regulator tells us that the generation capacity of rooftop solar is now more than 11,000 megawatts, which is actually almost 4 times what it was 5 years ago. And according to the Clean Energy Regulator, the trend is continuing. There were 3 gigawatts of rooftop solar installed last year, which was 40% up on 2019, and another 3.5 to 4 gigawatts of capacity expected to be installed this year. The Australian government tells us that we're now at about 24% renewables in the national energy market, with predictions of 50% more being added over the next 10 years. And commentators also note that in the media that the rapid growth of Australia's renewable technology is being stifled by grid limitations, and that probably won't come as a surprise to many of you. And it was first introduced or mentioned to me by one of our customers, a guy by the name of Frank Mayo at Electronet, something like 5 years ago. He said there was a problem looming, in particular with the wholesale uptake of domestic solar. The grid wasn't designed for it, and a solution was missing. And that comment from Frank all those years ago was kind of a light bulb moment and a turning point for GTS. And it kind of sounds obvious now, and Steve Hoffman, by the way, reinforced this a few years ago when he joined us, that as a company, we really need to seek out partners with specialist technology to supplement the core data infrastructure that we provided. So we could see more and more examples where something specialized was needed to deliver a complete end-to-end solution. And we wanted to be there to be able to provide that to our customers and not just the data infrastructure, if you like. So fast forward a couple more years, and GTS now has established great partnerships with specialist technology vendors, including PICE, with their world-leading DER and microgrid technology. And in partnership with PICE, we've been able to deliver the landmark Onslow DER solution at Horizon Power that you'll see today, creating a microgrid of the future that uses technology that really didn't exist back when the problem was first predicted many years ago. We're partnering with AEMO. We're partnering with PICE also to deliver AEMO's DER marketplace, and we're pursuing other opportunities in the APAC region: Japan, Guam, Taiwan. And interestingly, it's not just large-scale generation looking for solutions. There are large consumers of energy that are investing in renewable infrastructure to support their own needs. The folks at SA Water are doing some really brilliant stuff as part of a zero-cost energy future program. We're also consulting with Riverina Water in New South Wales that are exploring the idea of establishing and operating their own energy infrastructure to support their energy needs. So there's diversity in the marketplace for this. And those are just a couple of examples, but more broadly as a company, there's a great synergy and opportunity in the partnership between GTS as integrators and specialist technology vendors, where we're both aligned in creating quality outcomes for our customers. The technology partners bring the specialist tools, we bring the local integrator presence, and we invest in developing the skills in those specialist tools so that we can provide the ability to support the design and implementation of the solution and also support it afterwards. And that's very important to us. It's not just a set it up and walk away. We're here for the long run. We're here to learn those solutions and be able to support them in the long term. And I think we've seen in particular with AEMO and Horizon Power, that combination of our partnership working for a customer works really well for everyone. And so because of the growth in domestic solar and the challenges that brought, and the comment made by Frank Mayo from Electronet years ago, we changed our strategy to position ourselves that way, to be able to provide those end-to-end solutions and combine our technical capability with the wealth of experience and the specialist technologies that our partners provide. So today you can read in the Australian government's net zero plan that our country is relying on further technological breakthroughs that we don't know about yet to deliver on our net zero carbon target. But interestingly, an academic, a professor from the Australian National University, regards that up to 80% of our net zero solution can actually be achieved by eliminating gas and coal and moving towards electric vehicles. So the future is in a large part maximising the use of renewables and managing the mass introduction of electric vehicles. And I think, as you'll see today, that capability is not vaporware. That capability is already here, and you'll see that today. So let me reiterate Steve's thoughts there. Thank you again for attending, and I hope you all take something useful out of what you're going to see today.
Terrific. Thank you, Andrew. Chris, would you like to share your screen, please?
Yes. Thank you, Steve and Andrew. Bear with me one second. So thanks everyone for joining. As Steve and Andrew mentioned, I'm Chris Wycheck. I'm with PICE Energy Solutions based in San Diego, California. I just wanted to start off very quickly discussing who PICE is, where we're located before diving into some of those market and global DER energy needs that we're seeing throughout the world. So PICE, we are a software-based control solutions provider, currently have over 1 gigawatt of assets under control globally. We utilize a proprietary synchrophaser-based active control technology as the core brains behind our software platform, which integrates a wide variety of DERs and at speeds of up to 60 hertz at the point of interconnection. We are vendor neutral. We support over 450 energy asset and industrial communication protocols, and our team is tremendously experienced. You'll be hearing from our CEO, Patrick Lee, at the end of this presentation. Many folks like him with decades of experience in the utility and energy space are found on the PICE team. We have a global presence throughout the Americas and Asia Pacific at the moment. We have a great ongoing deployment with Horizon Power featured next, and we focus on a number of different energy control strategies. So throughout the world, we're finding that there's an increasing diversity of DERs in energy markets. In contrast to traditional centralized generation or storage technologies, these are increasingly distributed, increasingly of limited dispatchability. It may only be able to produce energy when certain resources are available, or of fixed duration, so they cannot run indefinitely like a battery storage energy system. There's a diverse landscape of third-party optimized control systems out there that integrate with all of these resources in different capacities and in different ways in which those assets integrate with the grid. Some of these transition from grid tied to islanded and everything in between. So as you can imagine, there's competing interests among stakeholders in this space. Distribution networks absolutely want to maintain a safe and stable grid. They want to make sure that DERs that are interconnected into their system are not causing any adverse effects on the operation of that system. Many customers conversely want increased levels of grid independence. They want to be able to produce their own power as they have available at their particular customer site. So there's a natural spectrum of interests at play that are really driving the need for a more cohesive control strategy across all of these different parties. In Australia in particular, there's a really very unique way in which the DER market is growing and expected to grow into the future. In contrast to many other markets globally, which are often dominated by large commercial and industrial customers, heavy infrastructure, government, military, etc. The bulk of growth is actually attributed to smaller scale residential and business systems throughout Australia at the country level. That is really interesting from a technical and economic standpoint. And the implication here is that a very sophisticated control system is going to be required rather than controlling, a couple of hundred large C&I or industrial sites. We're talking about thousands to millions of small systems. So that's a very interesting and sophisticated problem to solve. Oops. The lights went out on me. Sorry about that. As we consider how to approach the problem of controlling all of these different DERs in a harmonious way, there are a number of key technical challenges that stakeholders throughout the entire landscape need to be considerate of. Integrating new power system components, solar and wind perhaps may not be prevalent in a particular area, or energy storage as a dispatchable resource. So branching beyond certain asset classes and into new generation and storage asset types is something of strong interest that we're seeing throughout the world. Integrating new operational and control technologies within these solutions, integrating hybrid power plant control schemes, microgrids, integrating those systems with ADMS systems or other distribution network types of control schemes, very, very important. A lot of the integration for these new solutions requires networks, developers, and system owners to adjust their own business models and energy strategies within their organizations, making sure that it aligns with internal structures and processes. A lot of times these new systems are completely new, and perhaps finding a process to move it through internal approval structures is something that is a very serious organizational challenge to be worked through. The way in which these assets are controlled, how we control large quantities of customer-owned DERs versus something that's purely controlled from a network operator perspective, very important things to consider. Additionally, there's a range of broader policy questions, figuring out are the control of these assets something that we can recover the costs of through rate recovery? Is it something that's going to be passed on to individual customers via a service-based model, that type of thing. From a technical standpoint, the coordination of these many renewable assets is leading to very unique challenges, which I'll get into in a moment, at the transmission level, down to the distribution level, all the way down to the individual site level. So having a cohesive strategy that can span across that entire, top-down landscape of control is quite important. Some of the specific problems that we're seeing around the world relate to the intermittency aspect of some of these renewable generation resources and the need to provide very quick levels of control in order to mitigate some of the effects of those systems. In particular, we may find that in certain markets, spinning reserve resources are actually utilized more often than not to quickly correct deviations in frequency or voltage or other similar parameters. As we rely more and more on renewable-based generation, utilizing spinning reserve resources may actually not be quick enough, and we may have to rely on a higher speed inverter-based resource to provide some of those system services. So what you see on the left is a spinning reserve-based response to a frequency variance. And on the right, you see that same system being controlled via inverter-based resources. Similarly, the control systems may have to work around variations in weather in production and utilizing these same inverter-based resources to smooth out some of those control issues, or excuse me, some of those intermittency issues, something that's critically important for us. The way in which we've seen a number of technologies deployed to mitigate some of these technical challenges globally really falls into three main bins. And this isn't true that every case will fall into one of these three, but the majority can find one of these three that it most closely aligns to. So at the smallest end of the spectrum, we're finding microgrid level controls. So they're situated at a site or campus level, interconnected into a local low voltage or medium voltage distribution system, typically in the hundreds of kilowatts to tens of megawatt range. On the other end of the spectrum, we're finding a need for precise control at the utility scale with a power plant controller type of system. These are typically interconnected to a high voltage transmission system in the tens to hundreds or even thousands of megawatt range. What we find most interesting, and something that Lee and Patrick will dive into, is how these two different control strategies that I mentioned, the microgrid controller, the power plant controller, really interplay with one another when you're looking at them being interconnected into the same distribution level circuit. So having a means to issue commands to both microgrid controllers at customer sites or power plant controllers at utility scale development, and making sure that that distribution circuit or transmission circuit that they're interconnected to is operating in a stable and efficient manner That's where we find our DERMS product being a good fit. Our microgrid control software that we find installed at the site level really helps customers obtain front of the meter and behind the meter microgrids, facilitating that transition between islanding and grid tied systems, providing alternatives for networks in terms of non-wires alternatives or some type of utility controlled DER. It's a way for them to easily replicate a pattern of deployment over time to new assets. So what Lee is going to talk about in the next presentation, we're using that as a framework to potentially help Horizon include that development strategy to the deployment of other towns as well. So tying into Lee's upcoming presentation after mine, we wanted to talk about the Horizon Power and PICE DERM solution. So this was actually one of the first successful implementations of the emergent IEEE 2030.5 protocol, which a number of stakeholders have a keen interest in throughout Australia, particularly as it relates to dynamic operating envelopes and providing precise control at the distribution level to a number of different assets throughout that footprint. Our system is controlling hundreds of DERs across a couple of hundred customer sites and mitigating some of those intermittency and coordination challenges that I mentioned previously. So with that, I think I'm out of my allotted time, but wanted to pass the baton to Lee to speak about Horizon Power and the PICE DERM solution. Thank you.
Thanks, Chris. I'll just share my screen. Okay, so I'm here to talk about Horizon Power's DER management platform. And in particular, I'll introduce the Onslow microgrid and the Onslow DER project. And we'll talk a little about the DER management platform at a high-level architectural perspective. I'll jump into its application in Onslow at varying levels of control. So talking about the control philosophy, the control hierarchy, and coordination between these different streams of control. I'll show some performance trends from DERMS to give you an indication on how some of our control objectives are being met by the DERMS solution. And then I'll briefly discuss some of our expansion plans. Okay, so the Onslow microgrid, as you could see from the picture in the last slide, is a remote township in the Pilbara region of Western Australia. So it is a small township by the sea of around 900 residential customers. And really the Onslow DER project was all about Horizon Power building the microgrid of the future, and what this future really looked like from our modelling work from the planning engineers was a highly distributed renewable energy future, particularly from customer behind the meter solar systems. In addition to that, we were seeing already highly constrained parts of networks and microgrids due to reverse power flow from excess power, solar power during the day, and also limitations on step load capability of our generators, either diesel or gas gensets, due to the intermittency of solar generation. So in Onslow here, what we have is a power station, 7 1.1 megawatt gas engines, they're reciprocating engines. We have a utility battery there, which is for spinning reserve support, whilst the gas genset takes about 5 to 6 minutes to start up. And we have a solar farm connected to the 33 kV bus. Out in the network, we installed a smoothing battery around the same size as the utility BESS at the power station. However, it's larger energy content. And we have now close to about 3 megawatts of solar. So that's made up of a mix of residential, commercial, and also our solar farm provided by Horizon Power. We have a small number of battery systems at the residential level, and we have more smoothing customer best systems for those larger C&I customers. As you can see, the load, it is a small town, a small microgrid, around 4 megawatts peak load. Minimum daytime is about 900 kilowatts. So you think about, you know, we have 3 megawatts of solar during the day, and our minimum daytime load is around 900 kilowatts. So it's a significant imbalance that we need to manage. And we also, on top of that, have a highly variable industrial load of about 2.2 megawatts coming in and out as they will. So the DER management platform is what I like to call this solution stack, and all these controls sit on top of Horizon Power's operating and information technology server and network infrastructure. So we have the DERMS, and so the PICE DERMS and the PICE microgrid controller, or the advanced control technology, ACT, sitting on top of that server infrastructure. And then of course we've got the DER systems out in the field, and what links these DER systems to the DERMS is our what we call our secure gateway device, which is an IoT device provided by a company called Switched-In. And these are the players in our Onslow DER project. It's really worth noting that DERMS was really a concept and trial at the time when we wanted to implement a DERMS in Horizon Power, and particularly we see these issues arise on electricity networks much sooner than the larger interconnected grids, because of these microgrids are small. So important to note the highly collaborative nature of the way we had to work with PICE, GTS, and Switched-In in order to sort of work through the foundational challenges around building such a control system. And this project's been going for about 2.5, 3 years. We're about to finish up. So the DER management platform, so the DERMS, PICE DERMS, sits on a foundational layer of OSIsoft Pi data infrastructure and software. Then there's also a PICE proprietary modular control software that interconnects and interfaces with the Pi data infrastructure. We also, a main requirement for the DERMS was to be able to integrate. So on the left-hand side there, in the grey boxes, was to integrate with our distribution management system, Power on Advantage, and also our SCADA systems, systems on the SCADA network, sorry, AMI metering systems, a GIS system, and external weather forecast providers to provide that information that feeds into the DERMS optimization and load forecasting techniques. So out on the left-hand side, DERMS passes its commands through to via the IEEE 2030.5 SEP2 server through to behind the meter assets.
For that, they made comments on that. So you may have to be out there sorting clothes next to Republicans, so just prepare yourself for that.
Okay. And so that communications is enabled via Switched-In's secure gateway device. So that's that IoT device that connects on site at the residential at the residence, at the customer residence, for each behind the meter asset. We also connect to local microgrid, of course. So we have a microgrid controller at Onslow, for instance. However, the requirement for a DERMS in Horizon was about initially the trial was for Onslow, but we wanted to be able to expand this solution out to the rest of our microgrid portfolio. So in the future, we expect to see this DERMS platform operating and managing, controlling behind the meter assets across 34 microgrids across Western Australia's, across the region of Western Australia. And we've also enabled the build to also integrate with retailer or third-party DER aggregators. Control hierarchy was really a significant part of the planning process for building this DER technology stream. So I thought it's just important just to highlight how we approach this from a primary, secondary and tertiary layer of control. Primary at the milliseconds, secondary at the seconds, and tertiary at the sort of minute dispatch scale. In the traditional stream in the middle there, we have at the primary level, the power station asset controllers. So this is your generator governors and AVRs. It could be your transformer AVRs, and also, also the inherent inertia of the system, right? At the secondary layer, we have in Onslow the PLC, which is what we call the master station controller. And then we also have the COMAP that sort of sits on top of each COMAP IntelliGen controller for each of the generators. And at the tertiary level, obviously I've mentioned our generation and distribution management systems, PowerOn, and also Cytec. So those systems integrate with the secondary systems. On the far right, the DER technology stream, starting at the primary level, obviously we have a DER inverters providing frequency and voltage droop response and their droop response modes and specific device functions. We have the secondary level, the microgrid controller, PICE's ACT, providing real and reactive power control of both the smoothing battery at the zone substation and the solar farm, which you'll see on the next slide. And it also has the logic that facilitates the hydrocarbons on-off transitions. And now that also integrates and slaves to schedules provided by the DERMS. Now the DERMS can consume a lot of data from the network, from the SCADA network and from IoT platforms and AMI metering systems to provide a level of grid awareness across the microgrid. It from this information, it optimizes for a solution based on business rules and control objectives, and it schedules real and reactive power dispatch to each individual DER system. So the Onslow microgrid, this is what it looks like. Power station at the top there. As I mentioned, the power station BESS, providing spinning reserve support, and power is transmitted through those transformers through 17 kilometers of feeder underground cable down to the zone substation, which is then distributed through the reticulation network at 11 kV down to 415 volt. As I said, we've got about 2 megawatts of distributed solar on that LV network, and we've got that 1 megawatt solar back up at the power station. So just to recap on the layers of control, we have the COMAP across all those generators there, and the master station controller that sits a level above the COMAPs, and also controls secondary set points to the power station BESS for spinning reserve. And then we've introduced this DER technology stream from PICE. So what we have is the master DERMS, this concept of the master DERMS. That's server infrastructure sitting on our Bentley server rooms, so it's on-prem, and that dispatches to the behind the meter assets at 5-minute intervals. It also passes 5-minute real and reactive power schedules to the microgrid controller or system DERMS, which then that microcontroller slaves to those schedules. The microgrid controller is also a closed loop controller, so it will do what it needs to do on site every second or less, depending on what occurs across the point of interconnect there, as you can see. So DERMS performance. So this is a screenshot from HMI from DERMS. that we've built alongside with Pice, and this really gives us a high-level indication of what's going on across the system in Onslow from an optimization point of view. So we've got the top plot, which shows how many generators are online, and the second plot is actually an indication using predictive analytics in DERMS, indicates when a hydrocarbons off decision could be made. So that means that all generators go off and we're running at 100% renewable energy operation. So as you can see there, that purple trend indicates that there's about 7 to 8 hours of HOF period there that we could have run if we have had that commissioned, which we're actively working on at the moment. As you can see, I mentioned in the next plot, you've got the dotted yellow line, which shows the solar at around 3 megawatts. The other yellow lines and orange lines are the dispatch schedules for the PV from DERMS. And the hard orange line is the solar actual measured value. And as you can see, we're curtailing quite heavily this day to meet the control objective of keeping 2 generators online at their minimum generator loading, which is 500 kilowatts per unit. So it's 1,000 kilowatts. It's got to keep that hard line and not go below. And as you can see, it holds it pretty steady across that point of interconnect. And that's a collaboration between the DERMS schedules every 5 minutes and then the Pice MGC, mopping up the difference between any kind of real or reactive power excursions within that 5-minute interval. And the plots below just show what the utility smoothing battery was doing during the course of the day and how active it is in its discharge. And then there's and charge, and then there's a state of charge schedule there as well. And the way we have it configured at the moment as part of our business rules is to keep that battery as a smoothing battery, so we don't really need it to peak load shift energy from one point in time to the next. We have proven that works. However, we really want to prioritize the reliability of smoothing out power fluctuations across that point of interconnect, especially when we're operating at 1 genset.
Lee, you've got roughly about 2 minutes to go.
Thank you. And for the same day, this is another HMI from the DERMS product, which shows the group selection and DER group summary. So there's 4 VPPs or DER groups that DERMS is controlling in Onslow, and we've grouped them by kind of DER type. So utility, basic micro is all the residential mums and dads type 5 kilowatt inverter systems. As you can see there, we have 266 of those individual systems aggregated to about 1.3 kilowatts, megawatts, sorry. And as you can see there, it just gives you an indication of how the measured output tracks the PV schedule of DERMS. You can select the different VPPs across that top list there, which then will show you the different trends for those VPPs. And lastly, our platform is ready to be expanded on the back of the success of this pilot in Onslow. We're leveraging value engineering and lessons learnt from the 2 to 3 years that we've been implementing this project. And we plan to migrate DERMS. As I said, it's on-prem. We plan to migrate it to the cloud in around early to mid 2022. So plans are already in place for that. We're going to deploy as our ambition and corporate strategy is to achieve 0 refusals by 2025, and that means not telling customers they can't connect. So allowing all customers to connect their PV systems through any application coming through, and we can do that through the fact that we have a DERMS solution that can manage and curtail these systems when necessary. And then we're going to explore grid alternative and additional grid edge solutions, so our customers have more opportunities and more options. And so we want to integrate third-party DER aggregation And we also want to enhance our customer dispatch functions associated with the IEEE 2030.5 communication applications protocol. So load control, electric vehicles, and augmented with this concept of operating envelopes, so import and export at the customer point of connection. That is me done. Thanks, Steve.
Terrific, Lee. Thank you very much for a great presentation. Patrick, would you like to just take control over the screen, please, with your presentation?
Right. Before I do that, I want to make sure I check my microphone. Does this one come across better?
Yes, it does.
Okay, great. Okay, I'm sharing my screen. Can everyone see okay?
Yes, we can.
All right. Yeah, first of all, thank you very much for the opportunity to present to you the lessons learned from what we have done with Horizon Power. And what I think my job today is really help translate that learning into helping you to think about how you may go about addressing the DER challenges in your area, whether you're working with it or you have ultimate responsibility to take it to maximum integration. So briefly, I think the presentation will focus in maybe three categories, right? One is we'll continue with the story that Lee has presented, and then we'll talk about, well, what are the building blocks that we observe from that? And then what are the practical approaches? What should you do in terms of, well, where do you start first? And what do you need to know along the way before you get started so that you will manage a successful outcome? So to start with, I would say Horizon Power and Lee really had very advanced knowledge of how to operate a grid, particularly, I mean, in a lot of the remote community that they have operated, they truly understand the challenges and intermittency and other things. And I think the success that, to go from about 13% of the solar rooftop to more than 55% of the houses with solar rooftop is a pretty significant improvement, within a very short amount of time, deploying a combination of DERMS and microgrid technology there. And because they have two very small batteries, so that, truly, if you have more resources and able to store that, they can far exceed 80 minutes of running 100% on renewable without fossil generation, right? So I think there are enough, even though with very limited resources from the utilities ownership and direct control, primarily leveraging many of the customer DER resources, like Chris has mentioned, right? Unique for Australia, a lot of small DER integration, and makes it more challenging in terms of coordination. But I think the observation, or what is the building block that we observe that a remote community like in Onslow, how do you take that into other grids, particularly large regional grids? You'll see three things, right? Everyone, from a physical standpoint, you would have either one or more centralized location with generation or power sources where power comes from. And then you have a distribution network. I think in a modern power grid, of course, you have many distributed resources connected at the distribution level that really added the complexity that we're dealing with today that Chris mentioned and Lee reiterated. Now, you've seen this diagram roughly, right? That Lee presented. Well, generally, you can see, well, there's a source of generation, there's a network, and then you have integrated DER resources. This is a remote grid in Australia on land. Well, if you take this remote grid on land to a truly an island, based on our experience, whether you're in Pacific Island like Maui or American Samoa, whether you have one or two location or more locations of centralized generation, you still have these community-like network with distributed DER and I would say integrated to it. But what is unique about the generation source is that don't differentiate by the operating, I would say, building block of the physical system. think about how the power is actually managed at the generation source. In the case of Onslow and in an island, you're dispatching from a generator or eventually down to zero fossil generation. So at your generation point, you're really adjusting the power from some quantity imported into the network to down to zero. So either you're virtually islanded in a remote community or truly islanded in an island like in the Pacific. But if you translate that same physical model into a large network, you can think about that each area, a community, can be organized into a microgrid-like control system where you have generation sources. It could be the interconnection point to the grid or the substation of a point that traditional distribution system has. You have a distribution network of feeders and circuits where you have many DER integrated below in the low voltage network. The difference in building block between a large network and a remote island or a remote community is that they are islanded all the time. So the benefit in managing in a regional network is now not only you're managing from able to provide power resources to fit the localized network, or when you throttle it down to zero, you can rely on the DER providing power in a way you're virtually islanded in a network microgrid. If you think of this as a microgrid in a network, then you can imagine there a network of microgrids in a large network. The beauty of the operating mode is now allow you not only throw it down to zero to have a virtual island, but reversing the power to say, hey, if one microgrid has more power, so instead of the use case in Horizon Power curtailing, you can now reverse the power, feed it into the grid to share with another microgrid. So this is actually the learning from Horizon Power can enable us to manage networks of microgrid into large networks. So let's talk about, well, where do you start? So Horizon Power had implemented some larger utility scale solution batteries and community size solar. And then they also take on the path of managing customer DERs. What we have seen in Australia and North America is people may choose to take one path over the other, but ultimately they're going to need both capability in terms of control. You need to have engagement with customer and control their resources in order to maximize the benefit and return on investment of those DER. You also need to control utility larger assets in order to provide the reliability and then balancing that is needed. You can start with either one, and we have seen utility done that. But eventually, you ultimately would need more of the integration of these tools together if you're interested in drive higher percentage renewable. But a lot of time, when we're planning and looking forward in a utility, people do not see far enough. So the challenge is it doesn't matter which foot you're going to start first, right? If you know where you're going, you'll know that you'll need all of these levers. As you're putting more control lever into your control system, you will need all of them. And so the sequence of start at some point in time is not as important as to look at where your network is at and then make that decision. So we want to talk about, well, what's the first thing you need to know? Well, as you can imagine, in a large centralized grid, we know power only flows one way. But in a modern grid, power flows two-way. So in a modern grid, one way is really simple. Everyone knows what one-way traffic flow looks like, right? But when you have two-way flow, and when two-way flow occur, and it become more complex, particularly when you add in renewable energy that are intermittent. So generally, we have seen that utility around the world do not know what the operating mode looks like when they have a modern two-way grid, because they have not adopted a operating philosophy. Just like I said earlier, when utility don't know which step to start first, do they engage customer resources first or engage utility own direct control resources? If they didn't know eventually they need all of them, they wouldn't begin to think about, well, what's the ultimate control methodology, right? So that's why I think it's very important to understand the tool that's being deployed, and how do you actually, on a day-to-day basis, dynamically manage two-way flow, when EV move from one location to another, right? The second part is that, well, how advanced, when we talk about a network of microgrid that you see in a large regional network, how advanced of capability do you really need? So that's something that you need to decide on based on your network's capability. Because if you're running your network closer to the edge in terms of maximizing flow and voltage limit already, you certainly need a control system that's much more responsive and quicker. But if your penetration of renewable and DER is really low, you really don't need that in the beginning in terms of these advanced control capability. But you need to know and plan on what time frame you're going to need some more advanced capability that can both address the variability and also maybe even tied into the frequency-based control as the spinning inertia is decreasing and it could become more sensitive on both real and reactive power. One of the things you should think about is that oftentimes, many vendors will tell you, advanced distributed management system is your solution to address your DER problem, right? But truly understand what's driving what, right? In the traditional large grid, central generation drive transmission distribution. In a modern power grid, when you have hybrid, you have centralized power plant and you have many distributed DER, the dispatch of resources from the bottom drives everything else. So once you understand that, you say, well, what is the tool that drives the local resources locally? It's the DERMS, it's a distribution energy resource management system. A distribution management system is really a network management tool, good for planning and operation. So truly understand when someone say, yeah, I can have a network management tool embedded with resource dispatch and call it an advanced distributed energy management system. You can call that. Or some people will look at a DERM solution with network analysis capability also can solve a lot of problems, right? So really truly understand the capability of, is it really a VPP DERMS? Are you dealing with? Are you dealing with a demand response DERMS? Or are you dealing with more of a grid integrated DERM that does whole system forecasting like the one at Horizon Power? So really understand that. And also understand what maturity level that I touched on earlier on, where are you trying to go? Do you just need a DER registration process and support initial customer deployment? Or do you actually need to begin to run some VPP because you want a non-wire solution to be effective within your distribution system? Or you need to actually get to a point where you have both directly controlled DER in your customer program. You also allow your customer to participate through aggregators. For example, some of the project that we're deploying at AEMO is how do we enable DERs to participate in the market? Those all has to be all integrated to the localized terms. So know where you need to go. And finally, there are many pitfalls that we observe in utility is utility. I work in utility for more than 20 years, so I know that the drill, right? I think oftentimes we focus on one solution at a time. I'm going to buy a 2035 server. I'm going to just test it out, and then I'm going to integrate a DERM solution to it. I think this piecemeal approach has limitations. You really need to think through, and as you deploy technology, whether there's a path forward, whatever you put in first, do they really grow? Because otherwise you may have to revisit and rebuild, those solutions. So really pay attention on changing your mind about, okay, do I really need a solution at a system level? Because think about this, DER management is a system problem. It's not a linear problem that you can tackle one thing at a time. Whatever you do, changing the DER's integration to the grid, it affects distribution network, affects the transmission network, affects the centralized generation. So all of that has to be taken into account when a DERM solution is being integrated with localized microgrid and largely with a greater network. So ultimately, I think really important on change management is your operators are already dealing with many variables day to day. When you add in a distributed resource management system, it needs to be autonomous. It needs to serve them the schedule. They should be the pilot that's running the autopilot and not the one that's flying the plane, right? So that's something that really important in terms of the design of Durham solution that enabling less human intervention, because system is dynamic, it's complex, and it's very difficult to ask the operator to do more. And so I think these are the key takeaway that I want to share with you. We have a couple extra slides that added some additional information to share with you, but I wouldn't go into detail on that. Thank you very much for your time.
Terrific, Patrick. Thank you again. It really comes down to the time, so timing is well done, Patrick. So thank you very much. We're just probably around about 30 seconds to go, which is a good time that I'll just share my screen. So again, on behalf of PICE and Horizon Power and GTS, we would all like to thank you for your attendance today. A special thank you to Lee, who is actually doing the presentation while on leave. So thank you very much, Lee. We'd also like to just acknowledge that if you do have any questions post-presentation or post this webinar, please send them to me. We'll be happy to answer them. And also, if you have any further interest in what you have seen today, or you are contemplating a journey into the management of DERs in your network, which I think a lot of you are, please let us know. We'd be happy to sit down and talk with you and look at how you can approach that journey or start that journey to achieve an outcome which is going to be beneficial to you and your organisation. So in wrapping up, again, let us know how we can help. This GTS objective with these advanced technology webinars is to inform. We try to conduct these once every quarter, and we believe topics that have been presented today are very, very relevant. So please keep an eye out for future webinars. And on behalf of all of us here at GTS Pi and Horizon Power, thank you very much for your attendance today. Thank you, everyone, and hope to see you in the next one. Bye-bye.